Welcome back to the lectures on chemistry as part of the National Program on Technology Enhanced Learning, a program sponsored and funded by the Ministry of Human Resource Development. I have been lecturing on the basic principles of chemistry for the engineering students as well as students of basic sciences. In the last two lectures, we have got ourselves introduced to quantum chemistry principles, the principles that we will use again and again, and the principles that we will become familiar by examples. In the last lecture, the first and the simplest example, namely the particle in a box, was discussed. The relevance of the particle in a one-dimensional box, if you recall, I made an association with the energy levels of electron, to be more precise, in a conjugated polyene system. That is a linear system, motion is one-dimensional. Today we will generalize this to the motion of the particle in two dimensions. This is the course on engineering chemistry. My name is Mangala Sundar. I am from the Department of Chemistry in the Indian Institute of Technology, Madras, Chennai, and this is my electronic mail address, mangal@iitm.ac.in. This is the third lecture on the first module, atoms and molecules. We are studying the model problems in quantum chemistry. The free particle in one dimension was discussed in the last lecture. In two dimensions, the free particle energies. We will discuss that today, and the discussion continues from the last lecture. The contents of today's lecture, I hope that I can cover in the next 50 minutes or so, are the solutions for the particle energies in two dimensions and the wave function. This is the solution of the Schrodinger equation, time independent Schrodinger equation. The wave functions and the squares of the wave function will be represented by some pictures in this lecture. Pictorial representations or visualizations are very important in all of science and all of engineering. Wherever possible, we will try to draw a graph or give a plot of the surface of the wave functions if it is more than one dimensional, and so on. The second most important aspect of today's lecture will be the calculation of the expected values or the expectation values in quantum mechanics. From the last lecture, please recall that when we talk about experimental measurements, quantum mechanics comes up with a rule for the average or the expected value of whatever we are trying to measure through a formula. We will illustrate that formula in this lecture and follow that by examples with one or two examples to chemical systems. Given sufficient time, I would try to explain the Heisenberg's uncertainty principle, but in all likelihood this will go to the next lecture. Recall for yourself the one-dimensional particle in a box results. Let me quickly summarize these things from the last lecture. For a box of length L and the particle with no potential inside the box, the wave function was derived in the last lecture as √2 by L sin n pi x by L, where n is 1, 2, 3, etc. integers. The energy of the particle in the solution of the wave equation H psi is equal to E psi, the energies turn out to be quantized, discretized by the n's with a dimension with a unit for the energy h square by 8 ml square, where m is the mass of the particle, h is Planck's constant. So the result was particle energies are discrete, particle position inside the box is given by a probability description. This was the last lecture. In the last lecture I also introduced the Schrodinger equation for the particle in a two dimensional box in a manner analogous to the particle in a one dimensional box. Remember that the motion, the one dimension refers to motion in one direction, which we call as the coordinate x. A two dimensional box refers to motion in two orthogonal directions, namely a planar motion. The particle's position anywhere in a plane, the particle's energy due to the 2 degrees of freedom that it has, the wave function corresponding to these 2 degrees of freedom, for the special case that the potential in a certain region is 0 and it is infinite everywhere else. So the model was that we will solve this particular problem, minus h bar square by 2m dou square by dou x square plus dou square by dou y square times psi of xy, which is nothing but the kinetic energy times psi of xy, plus v of x comma y times psi of xy, which is the potential energy times the wave function. So what you have on this side is the Hamiltonian acting on the wave function psi, giving you the energy times the wave function psi. This A, please remember that we have been using the symbol L, so please replace in your notes that it is 0 to x to L, 0 to y to L, and the potential is infinity everywhere except the box. This is the model. Let us do a little bit of writing to see how do we solve this problem. Inside the box, the equation that we want to solve is minus h bar square by 2m dou square by dou x square plus dou square by dou y square psi of x comma y is equal to E times psi of x comma y. This is a partial differential equation, linear second order partial differential equation, second order dou square by dou x square. It is linear, there are no cross terms involving x and y. There is a method in mathematics called the method of separation of variables, which allows this equation to be solved quickly. Separation of variables. The variables here are x and y for the solution. According to this method, if we write psi of xy as a function, let me write the function using an appropriate symbol, a function capital X which depends only on x multiplied by another function y capital Y which depends only on y. This is possible by an examination of this equation, and this is from the calculus of the solution of the differential equation. We will adopt that and we will write down the solution for the wave function almost immediately. What is the role of this? The wave function is expressed as a product of two functions, each of which is a function of only one variable. Only one variable, and this, when you substitute in the differential equation, it allows you to simplify the differential equation very quickly. Therefore, when you write minus h bar square by 2m dou square by dou x square plus dou square by dou y square acting on a function x of x, y of y, giving you E x of x, y of y. Okay. This is a proposal for the wave function, that we assume that the wave function psi is expressed as a product of two one variable functions, one variable dependent functions. If we do that, what are the consequences? You know, this is a partial derivative. The partial derivative on x of course does not change the function y. The partial derivative on y does not change the function of x. Therefore, this equation can be immediately written as minus h bar square by 2m d square x by d x square times y, this y is a multiple, plus d square y times d y square times x, a multiple, and that is equal to E x of x times y of y. Now, if we divide both sides by x and y, the product x and y, the result will be minus h bar square by 2m 1 by x times d square x by dx square plus 1 by y times d square y by dy square. See, this is a capital X which is the function, this is the x which is the variable that this function is dependent on. Capital Y, it is a function of the variable y, and therefore this quantity is equal to E. It is a very simple method of separation of variables, and the argument now is that these two terms 1 by x d square x by dx square plus 1 by y d square y by dy square are two independent quantities. Therefore, this equation can be satisfied only when this whole thing is equal to a constant, this whole thing is equal to another constant, such that the two constants add to give you this value E. Therefore, the equation turns out to be minus h bar square by 2m d square x by dx square, you recall that there is a 1 by x, is equal to a constant E1 minus h bar square by 2m d square y by dy square times 1 by y is equal to a constant E2, such that E1 plus E2 is equal to E, the total energy. Please look at the solution here, minus h bar square by 2m 1 by x d square x by dx square, this whole thing is a constant E1, likewise the other term is another constant E2, such that E1 plus E2 is equal to the total E. Now, what does this tell you? This, you recall that the variable x is between 0 and L, the length of one side. Y is also the variable in the other orthogonal direction between 0 and L for a square box. You can have any other arbitrary box, let us stay with the square box to simplify things. So what you have here is now two one dimensional problems, two particle in a one dimensional box problems, exactly similar to what you had in the last class, in the last lecture. Therefore, the solutions of this can be immediately written down, with one exception. The exception is that, please remember this, that E1 and E2, each of which are given by independent quantum numbers. You recall that the energy is h square by 8 m L square times n square. These two equations are two independent equations. Therefore, there are two independent quantum numbers. E1 is proportional to n1 square, E2 is proportional to n2 square, another quantum number, does not have to be the same, except that the sum of the two energies should be equal to the total energy E. So the result is immediately obvious, namely E1 is h square by 8m L square times n1 square, E2 is h square by 8m L square n2 square psi 1 of x, which is x of x, you remember that is our notation, and that is going to be root 2 by L sin n1 pi x by L, exactly the same as the one dimensional problem. Psi 2 of y, which is the function y of y, is root 2 by L sin n2 pi y variable by L, such that the overall wave function psi x comma y is x of x times y of y, and the overall energy E is E1 plus E2. Okay. This is a result that comes from the use of an appropriate mathematical technique known as the method of separation of variables, which works well in this particular case because the equation is of that type. The partial second order linear differential equation in two variables does not have any cross terms, therefore the solution comes out like this. The summary of this result is the wave function now depends on two quantum numbers n1 and n2. You recall that is because of the x dependent quantity depending on a quantum number n1, the y dependent quantity depending on the quantum number n2, and the wave function is the product of these two functions, therefore it is indexed in general by two quantum numbers n1 and n2, such that it is x of x times y of y, and the energies are the sums of the squares of the quantum numbers, namely h square by 8 ml square times n1 square plus n2 square. That is what you have here. Let us just quickly see how to represent these wave functions in a simple pictorial form, and how to represent the squares of the wave function in a pictorial form, and afterwards we will examine the consequences of this solution in terms of the most important concept for today's lecture, namely degeneracy of the energy levels. Okay. What I have here are two plots. Let me go back to my notes. You remember x of n1 of x is root 2 by L sin n1 pi x by L. Since n1 is 1, 2, 3 etc., you have obviously x1 of x, you have x2 of x, x3 of x, and so on, all possible functions. Likewise you have for the y n2 of little y is root 2 by L sin n2 pi y by L, also running into the indices y1 of little y, y2 of little y, and so on. Therefore the wave function psi, which is a function of n1 and n2, let us take the first one, namely n1 is 1, n2 is 1, x comma y is obviously the product of x1 of x times y1 of y. Okay. You remember that this is a half sine wave, this is a half sine wave, both these half sine waves you remember you plotted them in the last lecture in one dimension. Okay. Now since this is a two dimensional function, to plot this function in two coordinates x and y, the value of the function in the third coordinates, the plot is obviously a three dimensional plot, it is not a two dimensional plot. That is the plot that you see now here. Psi 1 1 of x comma y, meaning n1 is 1, n2 is 1, is equal to 2 by L sin pi x sin pi y by L's, of course. This is a half sine wave. So if you are looking at this direction, this is the x direction, the orthogonal direction, this is the y direction. Therefore, if you plot this function sin pi x sin pi y by L in the graph in the computer, what you will get is a half sine wave. Like when you project this plot on this plane, you will get a half sine wave here. When you project this on this plane, you get a half sine wave, so you get a surface plot. It is a surface plot because it is a function of two variables. It is going to be a much more complicated plot if we are going to discuss the motion in three dimensions, like in the case of hydrogen atom, which is where we are going to go soon. If we take the square of the wave function, which you know represents the probability density, the square of the wave function in a small region gives you the probability of finding the system in that region. Therefore, if we plot the square of this wave function, you see you also get more or less similar plots, except that there is a little bit shallow on the ends, because sine square goes to 0 very quickly on both sides, and that is why you see the plot is slightly different. What is the next wave function? 1 2 psi 1 2. Psi 1 2 is psi n1 n2, meaning n1 is 1, n2 is 2. Along the x direction, the wave function is sin pi x by L root 2 by L. Along the y direction, it is sin 2 pi y by L root 2 by L. Therefore, you get a 2 by L. So what you have is a sin pi x by L sin 2 pi y by L, which tells you that along the x axis or the projection, this is a half sine wave, whereas in the y direction or in the y axis, if we project it, this is a full sine wave, and that is exactly what you see in this graph. Namely, it is a full sine wave in the y direction with up and down, and in the case of x direction, it is a half sine wave. That it goes through minuses and plus is because this function takes those values. But you see, when you project this on this side, you will get a sine wave, you get a complete sine wave here, and you get a half sine wave here. Now if you square this function, there is no negative part to this function, everything will become positive, and therefore the negative part, which is a dip that you see here, now becomes a nice positive lobe. This is now you see that it is a sine square wave. You recall the one dimensional plot again. You recall the one dimensional plot for psi 2 of x. You remember that it is a, let me do this here, and this is the node. Therefore, the wave function is, it's a sine wave, and the psi 2 x square, if you remember, the probability was that there is no negative part to it, that it is again in the middle, you have something like that, you have something like that. Okay. The negative part is squared up, and of course the shallow continues like that, and this is the kind of plot that you see along the y direction, and along the x direction you obviously see the sine wave, half sine wave. So this is the surface plot for the square of the wave function representing the probability density, psi 2 2. Now you know that it is 2 in the x direction, the quantum number n1 is 2, the quantum number n2 is also 2, therefore it is a full sine wave in both directions, and therefore you see the full sine wave form in both directions, and when you square them up, you see that correspondingly here that you see the two humps, this becoming, the negative parts becoming positive throughout because the function is squared up, and you see the two humps. This is quantum number 2, this is also quantum number 2. So the probability densities now very seriously change from region to region, from place to place. In a plane, there are regions where the particle is likely to be found much more certainly, and there are regions where the particle is less likely to be found. There is only a point or a nodal line where the density goes to 0, that is the square of the wave function goes to 0. you never talk about the probability of finding the particle at a point or on a line for a problem where the variable is continuous. You always take the probability density to be represented in a small region of space. Therefore, the probability density is never ever 0 in a region. It is very small. It is 0 at a point or along a line, but the probability in a certain region for finding the particle, whether it is one dimensional or two dimensional, is never 0, is never negative. Likewise for psi 2 3, quantum number in the x direction is 2, the first one. The quantum number in the y direction, the second one, is 3. Therefore, you should see a 3 sine half waves in the y direction and a 2 sine half waves in the x direction. And if this is not clear, when you square the function, when you square this particular function, you see immediately that there are 3 humps along the y direction when you see that, and along the x direction you see these 2 humps, indicating that this is the probability density function for the particle in a 2-dimensional box, a square box, with quantum numbers n1 equal to 2 and n2 is equal to 3. What is the other important consequence? Let us write the energy level expression once again. E is h square by 8 ml square times n1 square plus n2 square. For psi 1 1 of x comma y, the quantum number n1 is 1, n2 is 1. Therefore, E, let me also put the n1 n2 here to index the energies according to the numbers that we put in here. Therefore, E11 is 2 times h square by 8 ml square. Psi 11 is obviously 2 by L sine n1 is 1 pi x by L sine pi y by L. What about the next? Psi 1 2 is 2 by L sine pi x by L. You just saw that pictures a few minutes ago, sine 2 pi y by L. What about E12 is h square by 8 ml square, n1 square is 1, n2 square is 4, so you get 5 h square by 8 ml square. This is for n1 equal to 1, n2 is equal to 2. n1 is 1, n2 is 2. Now let me look at the case n1 is equal to 2 and n2 is equal to 1. These are possible quantum numbers for the system. The wave function for this state n1 equal to 2, n2 equal to 1 is different from the wave function for the state n1 equal to 1, n2 equal to 2. But what about the energies? E21 is obviously 5 h square by 8 ml square, but psi 21 is not equal to psi 12. This is precisely what is called the degeneracy of the energies of the system. That is, the system may have more than one wave function, may be represented by more than one state, but both of which have, or all of those states have the same energy. Such states are called degenerate states. E21 is equal to E12 represents degeneracy of order 2. It is not possible to have higher degeneracy here because we started with a 2-dimensional problem. The degeneracy in the case of a 3-dimensional system can be of order 3. You recall in the case of hydrogen atom, from your elementary descriptions of the hydrogen atom, the one s orbital is non-degenerate. The 2 s orbital is, of course, and the 3 2p orbitals, all 4 of them have the same energy. you know that the degeneracy in the case of the hydrogen atom is n square, where n is the principal quantum number that is associated with the hydrogen atom. You have studied that in the high school. Those conclusions will come out of this mathematics neatly when we do this hydrogen atom as we go through this process now. From a particle in a 1D to a 2D to a hydrogen atom, you will see how the degeneracies and these quantum numbers build up. The next important aspect for the model problems is how do we calculate average values for quantities that we measure. The energy, we know energy is a solution of the Schrodinger equation. We do not need to calculate the average values of energy. You will get already, when you do that, you will get the energies that you get out of the solution of the Schrodinger equation. But there are other things. There is momentum. In this model, of course, then the average position of the particle. How do we calculate them? Using the prescriptions of the quantum mechanical principle that we put forward in the first lecture. So how do we calculate the expected values or expectation values? For a particle in a one dimensional box, we will start with that and then extend to the same thing for a 2D and a 3D model. Remember that in quantum mechanics, every experimentally measurable quantity is represented by an operator. This is a statement from the first lecture. The average values in that lecture also was given as the integral psi star, the operator corresponding to what you are measuring, psi d tau divided by the psi star psi d tau. How do we do this for a particle in a one dimensional box? What is the average value for the position of the particle? For the position average, the verbatim formula, if you substitute, is the integral psi star x psi of x dx divided by the integral psi star x psi of x dx. Now we have to put all the integrals in the appropriate form. Now you recall, what is psi star of x or psi of x is root 2 by L for the particle in a one dimensional box. It is psi of x is root 2 by L sin n pi x by L. What are the values for x? X goes from 0 to L, one dimension. Therefore the integral, when you talk about the integral dx, the average value x is now from x is equal to 0 to x is equal to L, 2 by L sin pi x by L. If you want to put in an n, you can put an n for the arbitrary state psi n, x, that is the operator corresponding to the position, sin n pi x by L dx divided by 2 by L integral x is equal to 0 to x is equal to L sin n pi x by L sin n pi x by L dx. Psi star a psi d tau, psi star psi d tau, that is the average value. A here is x, therefore the position operator x. If we have to calculate the momentum, the average value for the momentum operator, you have to put the operator for the momentum between the two wave functions, that is sandwiched by the two wave functions. The operator for the momentum is minus I h bar d by dx. Therefore it is extremely important where you put that operator, and quantum mechanical rule tells you that the operator should be placed in the middle of these two wave functions, psi star on one side, psi on the other side. Do not ask me why, that works. There are no problems with that kind of a prescription when we calculate the averages. Experimentally we seem to have no inconsistencies of any kind. This is an elementary integral for you to solve. The average value of x in terms of the integral on the numerator and the integral on the denominator. Of course this you know, this is how you got 2 by L. Sin n pi x by L, sin n pi x by L dx was nothing but the psi square dx, which is the probability of finding the particle in a small region, and when you integrated the probability completely you got 1. Therefore this automatically is equal to 1 from your previous calculations. You only have to calculate the other. I will leave the result as for you to calculate, but the average value of x will turn out to be, for no one's surprise, L by 2, which is the middle of the box. No surprises here. What is the average value for a particle which is moving with a constant energy, kinetic energy between the ends of the box? Right in the middle. Okay. But what is the average value for the momentum of the particle? The average value for the momentum P is exactly the same formula, 2 by L 0 to L sin n pi x by L. Now the operator for P is minus I h bar d by dx sin n pi x by L times dx. You do not need the denominator because the denominator I showed you is already 1. Okay. So if you calculate this value for the momentum, which I would give you as a problem to solve, the answer is 0. The average value for the particle's momentum as it is moving in the box is, at every point the particle's momentum can be either this direction or in that direction, and therefore it looks like the momentum vectors all add up to give you, on the average, when you make infinite measurements. This angular bracket refers to the fact that it is an average over many theoretically or in principle infinite number of measurements. The average value for the momentum turns out to be 0. Okay. So this is how we become sort of operational in quantum mechanics. Now let us consider 2 numerical examples for the rest of lecture to illustrate why we have to worry about these things in the molecules and why we do not have to worry about these things in real life, in day-to-day life. Okay. Let us take 2 examples. Let me read the 2 examples again with the particle in a one-dimensional box model. The calculations for 2-dimensional boxes are very similar. So let us consider 2 examples of molecular systems as illustrative examples of the particle in a box model. The first problem, let us consider an electron confined to move in an atom in 1 dimension over a distance of 2 angstroms. So this gives us, since it is constrained to move in 1 dimension over a distance of 2 angstroms, the interpretation is that the box length is 2 angstroms. Neglecting the potentials due to other electrons and nuclei for the moment, which is equivalent to saying that inside the box that the particle is moving with no potential experienced by it. Of course there is in the atom there is a positively charged nucleus, and the electron moving in the absence of the positively charged nucleus is a fictitious problem. I mean, it is an imaginary problem, but let us assume, what we want to show is where quantum mechanics is important and where it is not. Okay. So let us assume for the moment that the electrons and the nuclei do not interact with each other. It is a very non-chemical assumption, but we will do that. Let us calculate the energy levels of the electron. How are they composed of? You remember that the energy level for the particle in a one-dimensional box is h square by 8 ml square times n square. So let us calculate that with the mass of the electron given as 9.11 times 10 raised to minus 31 kilograms. So mere substitution of the numbers. En is of course given by h square 8 ml square n square. H is 6.626 times 10 raised to minus 34 joule second, h square is square, and the mass of the electron 8 times the mass of the electron is 9.11 times 10 raised to minus 31 kilograms. The dimension given to you is 2 angstroms or 2 into 10 raised to minus 10 meters. It is L squared, therefore you have the square here, meter square. So you have kilogram meter square, and we want to calculate the energy, and at the top you have kilogram meter square second inverse square. Joule is second inverse square times second, therefore this unit is kilogram square meter to the power 4 and second to the minus 2. Okay. The result is number of joules 1.506 times 10 raised to minus 18 times n square joules, where n is the quantum number. Therefore the energy levels are separated by this factor. Now let us draw the energy levels. E1 is h square by 8 ml square, E2 is h square by 8 ml square times 4, E3 is 9 times this whole quantity h square by 8 ml square, and so on. So in units of this, if you call this as a unit of energy, E2 is 4 E1, E3 is 9 E1, E4 is 16 E1, and so on. Okay. Therefore the energy level diagram, if you draw, and if this is the increasing values of energy, if this is E1, E2, the difference between E1 and E2 is 3 E1, E3 is 5, the difference between these two, because E3 is 9 times, this is the difference, 3 E1, E3 is 9 times E1, and E2 is 4 E1. So the difference between the two is 5 E1. The next is of course E4 is 16 E1. So the difference is 3, 5, 7, 9, 11, and so on. So the energy levels increase with the spacing between the energy levels increasing. The difference between any pair of successive energy level is 2n plus 1, where n is the quantum number associated with that pair. Here it is 3, n is 1, 2n plus 1 is 3, n is 2, 2n plus 1 is 5, n is 3, 2n plus 1 is 7, and so on. Therefore the energies of the particle here are functions of n square, and the energy level difference is of the order of n. With this energy for the electron in the atom, 1.506 times 10 raised to minus 18 joule, it is a measurable energy. It is possible to distinguish such energies. So E1, 4 E1, 9 E1, etc. can be easily separated, can be understood. You can see them through spectroscopic measurements. Thus the discreteness that you have in terms of the energies can be directly seen by a spectrometer, by a spectroscopy experiment. Therefore the proof of the pudding is in the eating, as they say in English. The proof of the quantum mechanical calculation is the result that it gives, or measured or observed by the experiments and confirmed by the experiments. So these are perceptibly different energies. Let us take the next case where it is not possible to have such clear distinction. This country is mad after cricket, so let us take the cricket ball as an example. This is approximate distance. I am not a player of cricket, therefore I do not know the actual distance between the two ends of the stumps and so on. So approximate figure I am going to give you, 20 meters, maybe it is not, 22 yards, I do not even remember what it is. Let us consider a cricket ball, okay, mass of 250 grams, maybe it is heavy, light, I do not know, but it is of the order of magnitude, a quarter kg, okay, confined to move in a field of length 20 meters. Let us assume that the ball never flies off the batsman or off the bowler, that the ball is only between that region, and let us ignore the gravitation and all other potentials. Okay. Let us assume that the ball has only kinetic energy between the batsman and the bowler. Okay. What are the energy levels of the cricket ball? To give you an order of magnitude where quantum mechanics is important and where it is absolutely not necessary to go into such finer details. Again the energies are h square by 8 ml square n square. So what is our particle now? The particle is a cricket ball. What is the box now? It is a box of 20 meters and the two ends of the box are, one side is the batsman, the other side is the bowler. Okay. The ball does not go off either of them. Okay. That is not very interesting cricket, but we will just see that what that example tells you in terms of energy levels of macroscopic objects. Assuming that, and also leaving aside all the interactions that the ball has with the ground and so on, if we do the simple model calculation, you see what kind of energies we get. Much as the model itself is ridiculous, the energy levels are even more ridiculous. Okay. En is h square by 8 ml square times n square. H is a Planck's constant, you see this is 10 raised to minus 34 joule second square. Now the ball is 0.25 kilogram and the length of the box is 20 meters, therefore the length is 20 meters square times n square. So if you calculate all these things, you see that the energy levels are a number 0.549 times 10 raised to minus 69, impossible to measure no matter what the values of n are. Okay. N has to be at least 10 raised to 30, 10 raised to 40 in order for this energy level, these types of energy levels to be perceptibly different, which means that the discretization of the energies of this ball, the kinetic energy of the ball, when you consider quantum mechanics, the discretization is so small, so immeasurable that it is unimportant. The motion of the ball can very well be considered by a simple classical mechanical problem. We do not need the finer details of quantum mechanics. See, h is an extremely small number, 10 raised to minus 34. Its smallness is a large measure for the atom, where you have the other quantities also extremely small. The mass of the electron is 10 raised to minus 31 kilograms. The length, the atomic dimensions is 10 raised to minus 10 meters. Therefore you see that h square by 8 ml square becomes a meaningful quantity for the small value of h only when the masses and the lengths that you talk about are very small. When the masses are the masses of realistic values, the lengths or the dimensions that our eye can measure, you see that this discretization is no longer important, that the particle in the box is no longer relevant for the real physical macroscopic object problems. Perhaps that is the reason why it was never discovered. So the conclusion is that E1, 4E1, 9E1. What is 4E1 and 9E1 for this number? 4 times this, 9 times this. Of course you cannot see any of these numbers and therefore they cannot be distinguished by any measurement apparatus we have today. The energy levels of the cricket ball are continuous for all practical purposes even within this trivial model. What does this mean is that for macroscopic objects we do not have to worry about the fineness, the grained structure of the quantum mechanical equations. We do not need them. Classical mechanical equations are sufficiently accurate for us to follow the description. Let us review, having gone through the last 3 lectures, some new ideas and concepts which are quite foreign to us. Let us review them and I suggest some problems for you to do as a backup exercise to the lessons that are being broadcast. I suggest review problems based on what has been done up to now. The first one, derive the normalization condition for the wave function psi of x, particle in a one dimensional box. What does that mean? Show that the integral 0 to L sin square n pi x by L dx is equal to L by 2. This is the normalization condition, and this is what you used in writing the wave function as root 2 by L sin n pi x by L. The next problem is, does the wave function have a dimension? Like length, mass, time, does it have any dimension? If it does, what are the dimensions for the wave function for 1D box and 2D box problems? Can you generalize this to n dimensions? To n dimensions. The answer is the wave function has dimensions, but you can find out what the dimensions are, or please refer to textbooks accordingly. The third question is on the average values. The average value for the particle position x, you recall, is given by the integral 0 to L in one dimension 2 by L sin square n pi x by L times x dx. The value for x, what is x? The average value. Or if I give you the answer, verify that the integral gives you that answer. The answer is, of course, x is L by 2. Okay. The fourth one, think before you do this, what is the average value for the energy of the particle in the one dimensional box. Now, if you recall, our definitions for the average values A is psi star x A psi of x dx between 0 to L, because for the particle in the 1D box the denominator is, of course, is equal to 1. Okay. Let us write this out anyway. Okay. This is anyway equal to 1. So, when you talk about the average value for the energy, what is the operator that you want to use? You have to use the Hamiltonian operator. The operator associated with the momentum is the minus I h bar d by dx. The operator associated with the energy is, of course, the Hamiltonian. The operator associated with position is x. So, likewise, when you want to calculate the energy E, and if you put the Hamiltonian operator psi star x h psi of x dx. You should not be deriving the integral, but use the class lectures to write the answer immediately. Okay. That is a challenge. The fifth problem is calculating these quantities for the particle in a 2-dimensional box. These quantities like the average value of the position x, the average value of the position y, the average value for the momentum, etc., for the particle in a 2D box, 2D box problems. And lastly, of course, as a model, let me define an error in the position measurement by the quantity delta x, the error, as square root of the average of the square of the position minus square of the average value for the position. Please note this very carefully. This is the average value for the operator x square, and this is the average value squared. Calculate delta x, calculate delta x average. I should write this as the average value for delta x itself. Okay. Calculate delta x for the particle in a 1-dimensional box. Also, defining the average value for the momentum delta p as square root of p square average value minus the average of p squared, calculate delta p. What is your result for the product delta x delta p? These problems will serve as review problems for the last 3 lectures, and attempting them and solving them by your own will give you some confidence on the methods that will be continued further in the series of lectures. Thank you.